In this video, we're going to take a look at how do we actually compute these probabilities that are associated with a normal distribution or a standard normal distribution, and how does this process of normalizing or standardizing really work? What does it look like, right? Well, so basically, if our z is a standard normal random variable, right? We might be required to find probabilities like this. So let's say we want to find the probability that z is less than or equal to 1.25, or what is the probability that z is greater than 1.25, or what is the probability that z is between 1.25 and let's say 1, or what is the probability that our z is between negative 1.72 and like 2.03. So we might be required to ask to find probabilities like this, right? And we've had examples of all of these types before. Some less than or equal to, and or strictly less than, or some greater than, and some where our random variable is in an interval like this, right? With a number and a lower limit and an upper limit, right? Well, it turns out all of these, right? Again, we cannot even begin to use calculus for this. We have to rely on a table. So what we're going to do is look at what the standard normal table looks like that we will use, and then compute these particular probabilities. So I'm going to switch on over to another window and see if this works. Oh, there we go. I think we should see a table now. And in this table actually consists of two pages. The first page, it has negative z values. So you can see it starts at -5 here, and then it's negative 5.0, and then if this table allows us to look at probabilities of z values that are accurate to 2 decimal places, right? So we have the 5.0 here, and then we'll have like the 0.00, and then 0.01, 0.02, etc., right? So the first example, in fact, let's go back to our list to see what the first probability is asking us to find. It's asking us to find the probability that z is less than or equal to 1.25. So if we switch back to our table, then 1.25 would not be on this page because this has negative z values. Now if we go to the second page, which I have further down, then you can see it switches over to the positive values, and we are looking for 1.25. So in this leftmost column, I'm going to find the 1.2. So this is where we are. So the 1.2 is here, and then I'm going to go across to the column that has the 0.05. So putting this with this, it's 1.25, and then I find out where this row and this column intersect, and that is the probability. So the probability, and look, you can even tell, they even have a nice little picture up here that's showing you the area that's represented by all these probabilities here that are all accurate to 4 decimal places, right? So it's saying that if you want the probability that your standard normal distribution, look, they even have the nice fancy CDF. Our error function is right here, right? But we're not even going to look at this. It doesn't exist. It's too hard for us, right? If we want to find the probability that our random variable, our standard normal random variable, is less than or equal to 1.25, it's this probability, 0.8944. So let's write that down. So this is equal to 0.8944. Now for part B here, wants the probability that z is greater than 1.25. Well, that's nothing new for us. These are complementary events. In other words, either z is going to be less than or equal to 1.25, and this is the likelihood of that happening, or it's going to be greater than 1.25. So we can use our complement rule here and say the probability that z is greater than 1.25 is 1 minus the probability that z is less than or equal to 1.25. Now keep in mind, because we're working with continuous random variables, we can be a little bit loose in how we use the strict definition of the complement. Because again, remember, it doesn't matter if we include the endpoint or not. So whether there's an equal sign or not, right, the statement will be true. In fact, I could even just ignore the equal sign altogether and the statement will be true. That only works for continuous random variables, which of course our normal distribution is one of those. So we can find our probability in part B by doing 1 minus 0.8944. So that's going to give me 0.1056, right? So now what if we have a probability like this, where we're trying to find the probability that our random variable or standard normal random variable is somewhere between 1 and 1.25, right? Now, if you wanted to sort of visualize what this looks like, so let's say you have your little bell curve, your standard normal bell curve that looks like this. We know the mean is at 0. And so let's say this is 1, and then let's say this is 1.25. The area that we're going to use to represent this probability is this area right here, right? And the way we can figure out that green area is look at it this way. Take the area that's entirely to the left of 1.25, like that. So all of that, right? And then take the area that's to the left of the 1, that area, and take the difference between them. So take the red area that goes up to 1.25 and subtract the blue area that goes up to 1, right? And again, this is a calculation that we've done. So for instance, this probability is equal to the probability that z is less than or equal to 1.25 minus the probability that z is strictly less than 1, right? So it's that difference that we're using, right? Again, in some sense, it's like you're using the fundamental theorem. You see, like whenever you do your f of the upper limit, you're finding the area up to that point. And then when you do your f of your lower limit, you're finding the area up to that smaller number. And when you take the difference, you get the area between. And that's exactly what you're doing here. It's just that in order to find the numbers to take the difference now, we have to use tables. We can't use direct calculus, right? So let's see. So the probability that z is less than or equal to 1.25, this is 0.8944. We already found that one. So now we need to figure out what is the probability that our standard normal random variable is strictly less than 1. Well, let's go back to our table to see if we can find 1.00. So we're looking for 1.00, and that's right here. So that's 0.8413. So let's go write that down. So 0.8413. Take a difference there. What do we end up with? So the 3. So we have 1, 3, 5, 0, 0. So there is just a little bit more than a 5% chance that our standard normal random variable will take on a value between 1 and 1.25, right? So just kind of using that difference. For part D here, it's something similar, right? It's just that now one endpoint happens to be positive and the other endpoint happens to be negative. If you wanted to visualize this one, right? Again, we would have our nice little bell curve. Again, the standard one is always centered at 0. And so say 1, 2, so roughly about here is our 2.03, and then let's go this way, so -2, so then roughly about here, let's say here will be our -1.72, and what we're looking at is the area that's under our bell curve, right, from that z value to that z value, and we're looking for this, right? So we're going to do the same thing. We're going to find all the area to the left of 2.03 and subtract from that all the area to the left of -1.72. Now I will say something about these tables that I think are really handy. Some of the standard normal tables that are out there, they do not include the negative values. But this is a really good table. Hold on to this table in case you need it, not just in this course, but in other courses, because the fact that it includes the negative values, right? So instead of trying to use symmetry, which is what some other standard normal tables require us to do, we don't need to use symmetry to kind of figure things out. We can just go directly to whatever values are needed. So let's set up the difference and then get the values from the table. So we have the probability. So this probability is equal to the probability that z is less than 2.03 minus the probability that z is less than -1.72. All right, so we're gonna find. So let's first do the 2.03. So 2.03. We gotta scroll down some more. 2.03 is right here. So 0.9788. So this is equal to 0.9788 minus, and then let's find our -1.72. So here I have to go back up to my negative values. -1.72. So I see the -1.7 here. -1.72 is right here. So this is what I need. So I'm going to subtract 0.0427. Right, so 0.0427. So what do we get there? Well, we have a 1, we have a 6, we have a 3, and then we have a 9. So it's almost a 94% chance that our standard normal random variable will be in this interval, somewhere between -1.72 and 2.03. All right. So using if your problem is with respect to a standard normal random variable, then you immediately go to the table, and there's nothing else to do. But what if you have a different standard normal random variable? Or I should say a different normal variable. So suppose that it doesn't have a mean of 0 and a standard deviation of 1. Then you can't directly use the table. So we're going to have to use this process of standardizing. So let's take a look at this. And again, I'm not going to do any story problems here. We're just looking at a procedure. So let's say x is a normal, but now it has a mean of 50 and a standard deviation of 4.5. All right, so let's take a look at some questions that we can be asked regarding this random variable, which is we know it's normal, but it's not a standard normal. So let's go through and do a couple examples. So let's say part A, we wanted to find the probability that this random variable x is greater than 52, right? So again, we know the mean, we know its standard deviation, but we don't have a table that's specific to this. So the first thing we're going to do is to normalize or standardize this random variable and turn it into a z random variable. And the way we do that is by a simple two-step process. We subtract its mean and divide by its standard deviation. So that probability is equal to the probability that, so if we do this to the left-hand side of my inequality, then I have to do the same operations on the right-hand side of the inequality. So I have to take my 52 minus 50 and divide it by 4.5. And this now, when you take a normal random variable and subtract its mean, that's where you're now recentering it at 0. And when you divide by the standard deviation, you're rescaling its units and you're breaking it up into units of 1 essentially. And then so this automatically turns into our standard normal random variable, and then we have to compute what this is. Now if we take 52 minus 50, so that's 2, and then divide it by 4.5, so that should be 0.4444 recurring. Now since our table has z values accurate to 2 decimal places, we will round these numbers always to 2 decimal places. So we're going to have something like this, right? Okay, and that's fine. And if we want to do our complement now, right, so we can say that this probability is equal to 1 minus the probability that z is less than or equal to 0.4. And this is where now we're going to go to our table and find the cumulative probability that's associated with this z value. So let's switch on over to our table and find out what that is. So 0.44 is going to be on the positive side of our table. So there we are. So 0.44 is right here. In fact, let me go ahead and erase these since I don't need these right now since we're doing a different problem. So 0.44 is right here. Here we go. So the probability that our standard normal random variable is less than or equal to 0.44 is 0.67. So let's go back over. And then we'll have 1 minus 0.67. I don't need to write the other decimal places. You can if you want to. But this difference now works out to be 0.33. So there's roughly a 33% chance that this random variable, right, doesn't really have a special name, but we do know that it's normal, and we were able to standardize it and use our standard normal probabilities to come up with a 33% chance that x will be greater than 52. All right? Let's take a look at, let's say we have another one. Suppose we want to find the probability that our x is between and inclusive of 48 and 51, right? Again, the same process. We don't have a table for this, but we can standardize the probability by, again, subtracting 50 and dividing by 4.5, and now we have to do that to each part of this inequality. So this becomes the probability that my x is greater than or equal to, well, it won't be x in a second, but let's subtract 50 from each part and divide each part by our standard deviation, and then do that in the middle, right, 4.5, and then do that on the right. So we have 51 minus 50 over 4.5, right? So when we simplify the numerical endpoints, 48 minus 50, so that's negative 2 divided by, so now it's going to be a negative 0.44, so negative 0.44. And then this, we've standardized the normal random variable, so it becomes z. And then this will be 1 over 4.5, so that should be 0.22222. Yeah, so we're going to end up with, when we round it to 2 decimal places, 0.22, right? So let's write this now as a difference, right? So this probability is equal to the probability that z is less than or equal to 0.22 minus the probability that z is less than or equal to, and again, it doesn't matter if you have the equal sign or not, the negative 0.44, right? So let's first find the probability that z is strictly less than 0.22. So 0.22, that will be right here. So that's 0.5871. Let's write that down. So 0.5871, and then minus, and then the probability. Now, there's a lot of symmetry here, so look at what's going to happen. The probability that z is less than or equal to, okay, so let's find the, so here's our 0.4 or 0.04 column, and then let's go back down to the negative 0.4 row, so right here. So this is what we need. And look at that, it's the same 0.33. It's because of the symmetry that shows up in these nice bell curves. So we're going to subtract the 0.33, so 0.33, and then we end up with 0.2571, right? So that's the probability that this random variable is somewhere between 48 and 51. Now, let's kind of finish up these examples by looking at percentiles, right? Because that's, again, an important calculation that we've been doing quite a bit of recently. So let's say we wanted to find the 20th percentile of x. So the 20th percentile of the distribution of x. In other words, I want to find the little x and then the 0.2, right? Or 0.20 if you want to do that. Well, the thing is, again, we don't have a table for this x distribution. So the first thing we can do, we can find the z sub 0.2, right? So from our tables, let's get z 0.20, right? So again, it's just a matter of somewhere in the body in this table, we're going to, hopefully, if we can find exactly something that says like 0.2000, then we can figure out what the 20th percentile is. If that number isn't exactly in the body of the table, then we're going to have to find the closest thing to 20, right? So let's look at our table to see if we can find it. Well, it certainly will have to be in the negative side, right? Because we're looking at a percentile that is less than the median, right? So it has to be on the negative side. So let's see if we can find. Okay, so we're getting close. So down here we have. So we're looking at 0.20. So. Where is it? Well, this is probably the closest that we're going to get to right here. Right? Can't find I can't find another value that's closer to 0.2, right? So that ends up being negative 0.84, because this is our 4 column. Let's just go back up and verify. I'm pretty sure that was our 4 column, or 0.04 column. Yep. So there it is. So the closest we can get is this, right? So our z sub 0.2 is negative 0.84. So let's write that down. So this is equal to negative 0.84. That's fine, but we don't want the 20th percentile of the z distribution. We want the 20th percentile of the x distribution. So what we can do is use the same process that we use to convert an x to a z. We can then convert a z back to an x. So therefore, in fact, let's write it. I'm going to write down the equation that we will use. So this must be true, right? So the 20th, or what we're approximating it to be, it's approximately this. The 20th percentile of our standard normal distribution is equal to the 20th percentile of the x distribution minus its mean divided by its standard deviation. So now if I know what this is, I essentially can reverse, right, or unstandardize my my value and go back from a z value to an x value, right? So plug the negative 0.84 there, and then we have a nice little algebraic equation to solve. Right? So to unstandardize, you first multiply by the standard deviation and then you add the mean. So therefore, the 20th percentile of this distribution of x is equal to negative 0.84 times 4.5 plus 50, and then that comes out to be, what did that come out to be? 46.22, right? So again, what this means is in this particular distribution for x, remember we're saying that x is normal with mean 50 and standard deviation 4.5. It means roughly 20% of the entire distribution is less than or equal to 46.22, and then the remaining 80% is greater than the 46.22, right? So we still interpret percentiles the exact same way. It's just that now, again, we have to be reliant on our standard normal table to come up with the z percentile, and then use our standardizing process to work backwards to get our x percentile. Let's do one more example of a percentile. So let's say part D, let's say we want to find the 90th percentile. So what is the 90th percentile of the distribution of x? In other words, I want to know what specific x value has 90% of the distribution to the left of it, but only 10% to the right of it. So we're going to start from our table and get our z sub 0.9. Right, so from our table, we have z sub 0.9. Let's go back and see if we can find this. Now, the 90th, now that definitely has to be on the positive side. If you look down here, none of these probabilities are close to 0.9 at all. So we have to shift over to the positive side of our table. And okay, so again, let me erase some of the things we don't need. Let's get that off. So we're looking for now 0.9. Where could the 0.9 be? 0.9, where are you? Okay, so I see, so, okay, here we go. Yep. So the closest we're going to get, this is off by 0.10, well actually, yeah, 0, oh, 1, okay, so this would be, yeah, so this would be the closest that we can get to 0.9, right? No other value is closer, so well actually yeah, because then over here we exceed it by the 0.005. So the z value that corresponds to the roughly the 90th percentile of the standard normal distribution is 1.28, right? And that's actually a number that a lot of people know by hand. If you work with the standard normal distribution and you work with these percentiles a lot, some people they just know it. They know that, okay, for the 90th percentile of a standard normal distribution, it's 1.28. And then there's some other values out there that you know, like 1.96. You know, so they're just some values that are extremely important that you just know. So we got our 1.28. So that's that one. And then, so yeah, let's use our little trick. So therefore, the 90th percentile of our standard normal distribution is the 90th percentile of our not so standard normal distribution, or x distribution, minus the 50 divided by the 4.5. And then so we unstandardize. So we're going to take the 1.28, multiply it by the 4.5, add the 50, which is our mean, and that's going to be now the 90th percentile of the distribution of x. And let's see, so, and yeah, so therefore x sub 0.90, that's equal to 55.76. All right. So again, I really do like the fact, and I'll flip over one last time. I really do like the fact that this table has both negative and positive values. So you got your negative values there, and then you got your positive values there. And you can see that it gives, you know, to 4 decimal places, that's quite accurate, you know, for your probabilities. And then once you go, you know, beyond 5 here, you can see that so all these blanks essentially are 1, right? That's your CDF converging to 1 this way. And then on the flip side, on the negative side, if you go too far to the left, see how small the probabilities are getting now? Essentially all the other ones over here are 0, right? So it's really, you know, it's when you're within like you know, -4 to +4, that's when you tend to get, you know, I would say significant probabilities from your standard normal distribution. All right, well, there you go. So that's using our tables. We can use it to find probabilities. We can use it to, at the very least, approximate percentiles. Not a difficult process, but then now you know how to do it. And hope to see you in the next video.